You can actually share now.
Oh, you share now? Okay, great. Oh, good. Let me just quit out of this. Okay.
Wait for maybe 2 more minutes. One or two minutes.
Yeah, how have things been going? Oh,
it's good.
Oh yeah, good.
You also having another seminar. Should I advertise for your second seminar?
No, that one's. I mean, that's okay. That's just for that's just like a string theory group meeting. Like it's for the grad students who wanted to.
Yeah. Maybe more people also want to follow up. So you can mention that. I think you can tell the info if you want to. No worry, it's not a problem. Sometimes it's good to have a several discussion. I think it's good, actually good. No worry.
Okay, sounds good. Yeah, I can mention that briefly. Great.
Okay, we should start. Let me also create a recording.
Sure.
Welcome everyone to Harvard CMSA Quantum Math and Physics Seminar Series. It is our great honor to invite Dr. Jordan Cotler to speak today. He previously worked at MIT and Stanford for his PhD, and currently he's a Harvard Junior Fellow. And he will be speaking about his recent work on renormalization group flow as optimal transport. Let me remind the audience, please feel free to interact and ask questions. Interact with Jordan and ask questions during the seminar. And that is directly welcome, Jordan. So yours, please.
Thank you for the introduction, Juven. And yeah, so I'm going to tell you about this work that was done jointly with Simon Rezhikov, who is a postdoc in mathematics at Harvard. And the paper came out about a month ago. And the subject of the talk is renormalization group flow as optimal transport. And I'll talk about more precisely what I mean by renormalization group flow as well as optimal transport. The latter subject is one which is perhaps not so familiar to most theoretical physicists, but I hope to try to convince you over the course of this talk that it might be a tool that will be highly useful going forward. So let's begin with a brief discussion of the renormalization group. So the question which the renormalization group seeks to answer is, how does our effective description of a physical system change as we tune the precision of our measurement apparatus? Now, the renormalization group is one of the central engines of quantum field theory and statistical field theory, and is also essential to holography in the context of the ADS-CFT correspondence. But a question which we can ask is, what does RG really mean computationally or information theoretically? There's been work towards the end of understanding RG from a computational or information theoretic point of view, in particular in quantum information theory, in the study of so-called tensor networks. But what I'm going to posit in this talk is that there is another way of understanding the renormalization group flow, which is very illuminating, which uses tools from computation and information theory, namely the theory of optimal transport, which allows us to have more penetrating understanding of what RG is and how we can use it and how we can compute with it. So this is going to be the subject of the talk. And now let me tell you what the basic setup is. So for simplicity, suppose that we have Euclidean scalar field theory on RD. Namely, we have a map phi, which takes RD to R, which is our scalar field. That is, we're going to confine ourselves for simplicity to the purview of statistical field theory of a scalar field, an interacting scalar field in particular. Now, the theory is specified by a probability functional, p sub lambda of phi, which is proportional to e to the minus action with some overall normalization. And here, lambda, we can associate with our RG scale, or perhaps I should say our cutoff scale. Lambda, if you will, is the largest momentum scale that we have the ability to measure. Or equivalently, 1 over L, which goes like the momentum cutoff scale. L here is the smallest distance scale, which we can effectively probe with our measurement apparatus. So P sub lambda is our best effective description of the statistical field theory, given that we can only probe up to momentum scale lambda. And there's a beautiful subject called the exact renormalization group, which is a set of tools for understanding the renormalization group non-perturbatively. Now, often when we compute RG flows in field theory, we compute it perturbatively in the sense of both perturbatively in small couplings, but also in perturbation theory with respect to changing the cutoff scale, namely that we change the cutoff scale in infinitesimal steps. What the exact renormalization group allows us to do is to reason about RG flow in a non-perturbative fashion, both in the sense of large couplings and also in terms of large flows, or changing the cutoff scale by a large amount. Now, an ERG flow equation schematically takes the following form. It's that if we take the derivative with respect to the probability functional in terms of its cutoff scale, that is, we change the cutoff scale infinitesimally, the manner in which our description of the theory changes with respect to scale is captured by some functional on the right-hand side, where the functional is some relatively simple expression in terms of the probability functional itself and its functional derivatives. Typically, the right-hand side will only be a functional of the probability functional itself, as well as the first two functional derivatives. It usually doesn't go to higher functional derivatives, although in principle it could. And one of the most famous examples of such an exact renormalization group flow equation was due to Polchinski, building off of earlier work due to Wilson. Now, Polchinski's equation, written down in '84, it turns out can be written in the following fashion. So this is a result due to myself and Simon Rezchikov, is that the Polchinski equation, as well as, in fact, a large class of other exact renormalization group flow equations, can be recast in this somewhat remarkable way. Let me unpack what this means. Here, this is a gradient, which is a gradient on the space of probability functionals. So it's not a gradient on RD, it's a gradient on the space of probability functionals for scalar fields on RD. And in particular, the gradient is always computed with respect to a metric, and this metric in this case is an infinitesimal form of the optimal transport metric, or in this case, a Wasserstein-2 metric, which I will have a lot to say about in detail later. I suspect it might be unfamiliar. This S, the object which we are computing the gradient of, is a relative entropy between P and a background distribution Q, which I'll sometimes call the prior distribution. The interesting statement is that the renormalization group is equivalent to an optimal transport gradient flow. This result allows us to gain an information-theoretic understanding of what Polchinski's equation, various other equations by Wilson and others in the context of the exact renormalization group, to be able to better understand what they really mean and how to manipulate them, and moreover, how to simulate the flows numerically that these equations provide. So this is going to be the subject of this talk. The talk in particular will be divided into 5 parts. In the first part, I will provide a review of the exact renormalization group as well as of optimal transport. In the second part of the talk, we will combine these different tools, and I will derive this boxed equation that I showed you on the previous slide, showing that exact renormalization group flow equations can be regarded as optimal transport gradient flow equations with respect to a relative entropy. And then we'll discuss some of the properties that we find as a result. In the third part of the talk, we'll be able to use these RG flow equations couched in the language of optimal transport to derive new non-perturbative RG monotones. In the fourth part, I'll explain how this optimal transport formulation of RG flow lends itself to an interesting variational formulation, which is amenable to new numerical methods. And finally, in the last part of the talk, we'll conclude with a discussion. Let's begin with the first part, where I'll provide a review of the exact renormalization group in more detail, as well as the theory of optimal transport, which I suspect may be the less familiar of the two. So let's begin with the exact renormalization group. Let's in particular focus on an example due to Polchinski, perhaps the most famous example of the exact renormalization group. So let me recapitulate a version of Polchinski's argument. So suppose that we have a Euclidean scalar field theory with a source. Now, let me write down here the partition function of the Euclidean scalar field, where here our source is J and our cutoff scale is lambda. Now let's unpack the way that I've written down the bare action. We have our usual quadratic term, where we have our kinetic terms and our mass term. And here we have a kernel, which is going to provide us with an effective UV cutoff. In particular, k sub lambda of p squared is a cutoff function which goes quickly to 0 when p equals lambda. So that is, it decays to 0 very quickly. Once we're above the cutoff scale, it can either go to 0 or it can decay very rapidly in the regime that p is significantly larger than lambda. Now, what I mean here by k inverse is simply the reciprocal of this function, namely 1 over k lambda. So that's what k lambda inverse is supposed to mean, just the reciprocal. Now, what this does, the reason why we have such a cutoff function, a smooth cutoff function, is that it renders all of our correlation functions, which we compute in this theory, as UV finite. It gives us a UV cutoff. That is, if we compute, say, a 2-point function or 4-point function or anything else, we will bring downstairs factors of k lambda. When we compute the correlation function, we have an effective propagator that is cut off at scales for which p are significantly larger than lambda. We also have here a source term. This is the source j in the definition of the partition function. And we assume for simplicity that the source vanishes above the momentum space cutoff scale lambda. That is to say, if we take functional derivatives with respect to z of j, bringing down phi's, we are only going to access physics, namely correlation functions, which is below the cutoff scale. Finally, we can also include the possibility of interaction terms, where at the moment I have not specified the dependence of the interaction terms and their couplings on the scale lambda. Here, by virtue of this cutoff kernel, this smooth cutoff, I have, at least at the level of the bare action at scale lambda, specified the cutoff dependence of the quadratic terms, but I've not explicitly specified the dependence of the interaction terms. So Polchinski's basic insight is that there is a simple equation which expresses how physics is preserved below the cutoff scale when we perform a small step of RG flow. In particular, if we take the partition function and we change the cutoff scale by a small amount, then if we're only allowed to probe physics that is significantly or substantially below the cutoff scale, namely if J, for example, is cut off, the J does not touch field-theoretic degrees of freedom at or above the cutoff scale, then those correlation functions below the cutoff scale need to be preserved when we do a small step of RG flow. Now, the way that this manifests is that if we change the partition function by an infinitesimal amount, that the right-hand side of this derivative should be proportional to the original partition function. Namely, we should have a constant of proportionality which can depend on the scale lambda, but cannot depend on j. What this means is that the new partition function that we get still encodes all of the same correlation functions below the cutoff scale, because indeed the correlation functions do not depend on multiplicative rescalings of the partition function, so long again as c does not depend on j, it only depends on lambda. So this is the equation which we are going to attempt to understand and to use to understand the explicit dependence of the interaction terms on the cutoff scale. So let me be more precise. Let me write out the left-hand side of this equation more explicitly. I've taken the definition of the partition function that I just showed you, and I've just taken its derivative with respect to lambda and expanded it out. This is, of course, what you get. We have, as before, this explicit dependence on the explicit lambda dependence for the quadratic terms, but for the interaction terms, we do not yet have the lambda dependence specified. Now, the question that Polchinski asks is essentially tantamount to a Jeopardy type question. He asks, is there a functional differential equation for this quantity, namely the interaction terms, such that star is satisfied? In other words, if I want this star equation to be true, is there a way that I could enforce this by having the interaction terms change in just such a way that the right-hand side organizes to be proportional to the original partition function? Now, it's not a priori obvious how to do this. Hold on one moment, I can address the question. But Polchinski provides an interesting solution to this constraint in the form of what we call the so-called Polchinski equation. He shows that if the interaction terms change in a particular way with respect to scale, if they change in a way which depends on two functional derivatives of the interaction term in the manner which I have written here, then it is the case that the right-hand side of this equation here conspires to be proportional to the partition function. Yes, there's a question.
Yeah, sorry, probably a naive question, but I'm just wondering, the right-hand side of the equation in the box, can we not have like nonlinear terms, like the partition function square appearing? Is that possible, or?
Well, how do I say I just mean to say that the partition function is unchanged. If you have the partition function squared and you take the derivative with respect to j, you're going to pull down other funny factors of phi. You're going to get a different definition of what you mean by correlation functions.
Right,
all I mean is,
yeah, but I'm just wondering, because you're arguing for the validity of this equation by saying that, oh, we're only probing energies lower than the cutoff. But does that forbid like nonlinear terms? I mean, I can still have like higher order correlations below the cutoff, right? Or
oh, I see what you're asking. Well, maybe let me say it in the following manner. So it's the case that this is a sufficient condition. It's not necessary. You can imagine that there is that there is potentially something more complicated that happens, but at least we can agree that this is a sufficient condition. And a sufficient condition is enough to be able to run through the logic of Polchinski's equation. Perhaps we could talk about later exactly, I think perhaps there's a bit of confusion about exactly how one would modify this. Perhaps we would disagree on exactly what we mean by modifying in a nonlinear way, or what's the most natural way of modifying a nonlinear way. But so long as this is sufficient, that will be fine for the purposes of this exposition.
okay, thank you.
Sure. Okay, so let me rewrite the Polchinski equation in a slightly different manner. So I'll rewrite the Polchinski equation not in terms of the interaction terms, but in terms of the probability functional. Namely, the probability functional is the object which is proportional to e to the minus s lambda. Now let me compress the notation slightly. I'll just compress the kernels into this object I'll call c lambda of p squared. And what we immediately observe is that the Polchinski equation actually can be written in the form of a convection diffusion equation. Here, we associate the time parameter of the convection diffusion equation with minus log lambda, where again, lambda is the cutoff scale. Now let's compare. Indeed, if we look at the right-hand side here, we see that there is a Laplacian term. Here we have an analog of an infinite dimensional Laplacian. And here we have the convection term, which is a gradient contracted with a vector field against p t. Here we have indeed a gradient, a single functional derivative, which is contracted with an infinite dimensional vector field. Here we have a finite dimensional index contraction where we sum over i's. The analog of it here is that we have an integral over p. It's like p is like a continuous index. Now, the relationship between the Polchinski equation and heat type equations has been noticed for a long time, potentially even as far back as Polchinski himself. But it's going to be important to keep in mind that there is this very particular connection between the Polchinski equation written in this manner and a convection diffusion equation. Let's just clock that for later. Now, there's a more general framework than the Polchinski equation for understanding exact renormalization group flows. It's perhaps less familiar. It's called the Wegner-Morris flow equation. So here's the form of the Wegner-Morris flow equation. This is an equation which was originally conceived in various forms by Wegner in '74, but was really established and crystallized and utilized in the work of Morris starting in the mid-90s, and in particular by him and his collaborators in the first decade of the 2000s. So this equation is slightly funny looking. It's not it has the form of a exact renormalization group flow equation, because we're taking the derivative of p with respect to lambda on the left-hand side, and the right-hand side is doing something to p. But it's less obvious than the Polchinski equation what it's doing. But in fact, it has a very beautiful and simple interpretation, which is that the Wegner-Morris flow equation is inducing a reparameterization. The infinitesimal form of the equation is that it just takes phi and it maps it to phi prime, where phi prime is related to phi by a reparameterization of delta lambda over lambda times psi of lambda, this object appearing here, which can be a nonlinear functional of phi and also the position x. So that is to say, what all of this equation is doing is it's inducing an infinitesimal reparameterization. Now, if you think about this, let's think about this taking a step back for a finite dimensional probability distribution as opposed to a functional probability distribution. So if we have a flow equation like the heat equation, okay, we have some distribution on Rn, say, and as we do an infinitesimal step of heat flow, the probability distribution changes in some continuous way. Now, one way of inducing that change is by a reparameterization, that an infinitesimal step of heat flow can be regarded as a certain kind of reparameterization of the probability function. Now, this is essentially an infinite dimensional analog. It's saying that the way in which a probability functional changes under RG flow is by a reparameterization, namely that the way in which the probability functional changes as we change by a small amount of scale is by changing phi to phi prime and then changing the probability functional by an overall Jacobian factor, as you're supposed to do for probability functionals. What's interesting is that Morris essentially established with his collaborators that most of the existing, if not all of the existing exact renormalization group equations can be expressed in this form. Now, notice that this has the form of a nonlinear vector flow equation. That, again, where we associate t with minus log lambda, the way in which p is changing with respect to t is by a gradient of a vector field, vi, multiplied by the probability distribution. Here, what's interesting about this kind of vector flow equation is that vi can have a nonlinear dependence on the probability function itself. Here, this is to say that psi can also be a functional of the probability functional. So this, you can think about this as just a more general framework for producing solutions to the Polchinski type equation. In other words, I told you the Polchinski had a particular ansatz that he was able to use to find an exact renormalization group flow equation, which was local in momentum space, but also preserved correlation functions below the cutoff scale. You can think about the Wegner-Morris flow equation as a much more general way of finding solutions to that constraint that encapsulate, but also go beyond the Polchinski equation. Now, I don't want to bring too much attention to this because this is a little bit in the weeds, but I just would like to point out that for a particular choice of this reparameterization kernel psi, and again, the details of this are not particularly important for the moment, then we can precisely recapitulate or reproduce the Polchinski equation. So the Polchinski equation is a special case of the Wegner-Morris flow equation. So now let's turn to a different subject, namely the theory of optimal transport. Now, it's unusual in a physics talk, hopefully my little picture is not blocking the citations here, it's unusual in a physics talk to be able to cite a paper from 1781. Perhaps citing a paper from 1939 is slightly more typical. But in fact, the subject of optimal transport goes all the way back to 1781 and was developed by Monge, in particular, maybe a decade later in the wake of the French Revolution. Now, let me give you the basic problem of optimal transport. It's a very down-to-earth type problem. Suppose that you are in a field in which there is a configuration of mounds of dirt. And what I task you with is taking the mounds of dirt as they are and reconfiguring them, say, into a different configuration of mounds of dirt that I specify. So there's an initial configuration of mounds of dirt, and then I give you a desired configuration of mounds of dirt. And I give you a shovel, and your goal is to reconfigure the dirt into the new configuration while expending the least amount of energy possible. So here would be a very bad way of doing it. Suppose you took all of the dirt and you took and you shoveled it into one huge pile, and then you took all of the dirt from that huge pile and you reallocated it into the desired configuration. But clearly, this is not the most efficient way of doing it. What you should have done is something more clever, in which you took the different mounds of dirt and you didn't aggregate them into a large pile at an intermediate step, but you instead reallocated them directly in some way into the desired configuration of mounds of dirt. So let's try to formalize this idea. So suppose that we have two probability distributions. Here, I've just written them on the real line for simplicity. And we have an initial probability distribution Q and a final probability distribution, initial P and a final Q, which correspond to two different configurations of mounds of dirt. Now, we also are going to have a transport map, which is going to be a map, in this case, from the real line to itself, but more general from a space X to itself. And we would like to have the constraint that the push forward of P under T is equal to Q. That is, that we are going to perform some transformation, some procedure to transport the dirt from one configuration to another, which is going to induce a map from the initial configuration of dirt to the desired final configuration of dirt. And finally, we have a cost function, which tells us the energy that we expend in moving a little bit of mass at a position on R to a terminal position, maybe a different position on R, which maybe is something like the distance between those 2 points. The optimal transport problem in the Monge formulation is to minimize over the space of transport functions satisfying this constraint, and to minimize in particular this energy. This is the energy cost of transporting an amount of the probability distribution P into Q using this transport plan T according to this cost function. So this makes sense if we have some distribution of mass or dirt under the probability distribution P, and we transport an infinitesimal amount of mass from position X to position T of X. This is going to be the total energy which is going to be incurred by that transport plan. And the idea is to minimize it, to have the most energy efficient plan in doing so. Now, this applies to more abstract types of problems. For instance, the context that Monge eventually had was also transporting artillery. This was ultimately taken up by Kantorovich in a more sophisticated context in the wake of World War II, also related to matters of transporting weapons or various pieces of cargo across Europe. But at least this is the most abstract formulation of the problem, or at least one of the most abstract formulations. So let me give you a slightly different formulation of the problem, which is due to Kantorovich, which is a bit more flexible. Now, suppose—
I have a question.
Of course,
Jordan?
yes. Mm-hmm.
What's the analogy for the cost, this function in the earlier, maybe the Polchinski or other RGE you try to show? What's the corresponding?
I will get to that shortly. Yes, there is an analog of the cost in the Polchinski flow, but there's a few things additional that I need to say to connect the dots between the optimal transport and the Polchinski flow.
Okay.
So yeah, that's up. Perhaps you can ask that in a little bit, and I'll surely get back to that.
Thanks.
Great. Okay, so the Kantorovich formulation is that we have an initial and final distribution, again, P and Q, but now we have a transport kernel. It's a slightly different way of phrasing the problem. We can think about the transport kernel as the amount of mass that we attempt to transport from position X to position Y. So the transport kernel has to have the property that it marginalizes on its Y coordinate to P of X. That is, if we integrate out Y, we should get P of X. And if we integrate out X, we should get Q of Y. So that is that it is a valid way of transporting the P distribution into the Q distribution. And likewise, we have our cost function. Now, the Kantorovich functional of pi is just the integral over x and y of pi of xy c of xy. In a way, it's a bit more intuitive. It's saying that if the cost of taking some mass from x to y is c of x comma y, and the amount of mass that we move from x to y is pi of x comma y, then this is indeed the total energy cost incurred by implementing this particular transport plan. Now, the reason for this Kantorovich formulation is that it is a relaxation. What that means is that there are certain probability distributions P and Q, I'll tell you an example in a moment, for which the Monge problem does not have a solution, but the Kantorovich problem does have a solution. So it's the case that whenever you have a solution to the Monge equations, you likewise have a solution to the Kantorovich equations, but not conversely. In other words, there are solutions to the Kantorovich equations which are not satisfied by the Monge, which simply do not have a Monge formulation. Let me give you an example. Suppose that P is the sum of two delta distributions, where we have, a delta distribution, say here, and a delta distribution here. And Q is a single delta distribution. Well, it turns out that one can check that the Monge formulation actually does not have a solution to the transport problem, but the Kantorovich formulation does have a solution to the transport problem. In fact, in practice, the Kantorovich formulation is the one which is most often used because it is more flexible and has actually, this optimization has a nice interpretation in terms of linear programming. Now, the Kantorovich formulation allows us to define a particular metric on the space of probability distributions. The one that will be the most useful to us is the one which is called the Wasserstein-2 distance. Now, in fact, this was not originally written down by Wasserstein. It was originally written down by Kantorovich, but for various historical reasons, it is called the Wasserstein-2 distance. What it is essentially the optimized version of this Kantorovich functional. Namely, we have a transport plan which what it means for pi to be in gamma of PQ is that it's a distribution pi which marginalizes to P on one of its coordinates and marginalizes to Q on the other coordinate. So this is just a shorthand notation for this property up here. Where we take the infimum of pi on this space over the Kantorovich functional, basically over the total energy cost, where we have replaced C by the distance squared between X and Y. And outside of everything, we have put an overall square root. So this is called the Wasserstein-2 distance. There's also the Wasserstein-P distance in which this 2 is replaced with the P and this 2 is replaced with the P. Namely, we would have a 1 over P. It's like an LP type distance. This Wasserstein-2 distance is nice because it has a lot of very favorable properties. So let's now turn to a different aspect of optimal transport, which is a bit surprising. Now, to preempt it, I need to tell you a bit about the heat equation. So the heat equation famously can be written in this form. It's just the derivative of P is equal to the Laplacian of P. And there's a very old fact about the heat equation, which goes back, I believe, to Dirichlet, although I think it perhaps was known by Gibbs as well, in which we can write down this energy function, which is in a certain sense like the kinetic energy stored in P, which is 1/2 times the gradient squared of P. And we can express the heat equation as a gradient flow with respect to the energy functional. So in order to do this, let's write down more explicitly what we mean by the space of probability functional, or by probability distributions. We'll regard the space of probability distributions on X as C infinity functions on X, which are greater than or equal to 0 and which integrate to 1. Now, the tangent space to the space of probability distributions on X is smooth functions on X, which integrate to 0. Now, how can we understand this? Well, if I take a probability distribution and I perturb it, say I take P to P plus eta, where eta is an element of the tangent space, then it should be the case that the integral of P plus eta should be equal to 1, because it's a normalized probability distribution. Since the integral of P is already equal to 1, then that means that the integral of eta must be equal to 0. So that's intuitively why the tangent space, the space of probability distributions, has this property that the tangent space elements must integrate to 0. It's so the probability distributions, the total probability is conserved under doing perturbations. A natural Riemannian metric on the space of probability distributions, or rather on a tangent bundle, is just the L2 inner product. That if we take two elements of the tangent space, we can simply take their L2 inner product, and this defines a Riemannian metric on the space of probability distributions. What's interesting, an interesting fact, is that if we take the gradient with respect to this infinite dimensional metric on the space of probability distributions, if we take the L2 gradient of the Dirichlet energy functional, what we find is a short computation establishes that we get minus the Laplacian of P. What's interesting about this is it means that we can recast the heat equation in this form to show that the way in which the probability function changes as a function of time is by minus the L2 gradient of the Dirichlet energy functional. In words, what this means is that heat flow is a gradient flow with respect to the Dirichlet energy. That is to say that the Dirichlet energy is a monotone under heat flow, namely that the energy dissipates. You can roughly think about it as that the kinetic energy is turning into heat energy, but more simply said that this quantity is monotonically decreasing under heat flow. But moreover, what's interesting is that the heat flow is completely controlled, completely governed by a gradient of the Dirichlet energy functional. This is an interesting fact, which was probably known in the 19th century, I believe, probably almost in the present form that I gave it, although the notation was a bit different because Riemannian geometry was not as widely appreciated at the time. What I'm going to tell you is something which is a surprisingly modern development. Even though the previous fact I told you was known probably in the 19th century, let me give you another interpretation of heat flow, which was only known as recently as 20 years ago, due to the seminal work of Otto. So it's been known for a long time, also since the 19th century, that the differential entropy is monotone under heat flow, namely that the entropy increases under heat flow. It's a basic fact that we learn in courses in statistical mechanics. But what's more surprising, in fact, is that there's a way of writing the heat equation is a gradient flow with respect to the differential entropy. So let me explain what that means. Let's consider a different Riemannian metric on the space of probability distributions, namely not the L2 one, but one that's a little bit more seemingly unfamiliar. I'll suggestively call it the W2 inner product. What the W2 inner product is if we take two elements of the tangent space, then it's the integral of P against the gradient of eta1 bar dotted with the gradient of eta2 bar, where the relationship between eta and an eta bar is that an eta bar satisfies this differential equation. In other words, eta bar is defined in terms of eta in terms of this differential equation. In fact, eta bar is uniquely specified up to an additive constant. But the additive constant doesn't matter because we're going to take a gradient of eta bar anyway. So this seems like a weird Riemannian metric to define on the space of probability distributions. But what's remarkable about it, which was established by Otto, is that this is in fact an infinitesimal version of the Wasserstein-2 distance. Namely, the Wasserstein-2 distance, which I showed you before, provided us with a distance on the space of probability distributions. What's surprising is that its infinitesimal form has a Riemannian interpretation, which in fact is precisely equivalent to this slightly peculiar looking inner product on the tangent space of probability distributions. In any case, perhaps even more surprising is that the infinitesimal version of the Wasserstein-2 distance has the property that if we take the gradient on the space of probability distributions with respect to the Wasserstein-2 distance, i.e. according to this Riemannian metric, if we take this gradient with respect to the differential entropy, this actually equals the Laplacian of P. That is to say, we can write the heat flow as a gradient flow with respect to the entropy. So not only is it the case that the entropy is monotone under heat flow, that the entropy is increasing, but in fact, the heat flow is completely governed by a gradient flow of the differential entropy with respect to the Wasserstein-2 distance. Now, this kind of connection has been quite important in PDE theory in the last 20 years and has led to at least one Fields medal, where ideas or convection diffusion type equations have been recast in the language of optimal transport theory to great effect, in which tools from the different subjects can inform each other and have enabled the derivation of surprising results of connections. But now we can start to see how everything pieces together. So let me give you the flow of logic so far at the level of syllogisms or transitive properties, if you will. I've established early on that the Polchinski equation is a type of heat flow, in particular a form of convection diffusion equation. What I've just argued to you here is that heat flow, at least some forms of heat flow, can be written as an optimal transport gradient flow with respect to an entropy. So if at the level of a syllogism, we might anticipate that the Polchinski equation maybe is a form of optimal transport gradient flow with respect to a type of entropy. Now, in fact, this does not immediately follow from anything that I've told you so far in particular, because the Polchinski equation is really an infinite dimensional functional equation. It's a particular type of convection diffusion equation, which is not the traditional type of PDE for which this optimal transport problem is studied. But nonetheless, we can see that there is a suggestive connection between an exact renormalization group flow like the Polchinski equation and an optimal transport gradient flow. So this is the kind of connection which we will attempt to make precise very shortly. So now let me go to the next part of the talk, in which I will discuss how the renormalization group is a form of optimal transport gradient flow. And also the question that Juven asked earlier on about what is the right analog of the Wasserstein distance on the space of field configurations, that will be addressed. What we require, in fact, is a functional generalization of optimal transport, since we're thinking not about probability distributions on Rn, but about probability functional for fields on Rn. So suppose we have initial and final probability functionals, P1 of phi and P2 of phi. We again, in similar spirit, have a transport kernel, which tells us how much field mass, if you will, we are going to transport from phi1 to phi2, with the property that it marginalizes on its second field to P1 and on its first to P2. So namely, it has this analogous marginalization property as our transport kernel's finite dimensions. And we also have a cost functional, which now is a map from field configurations to field configurations, across field configurations to R. So it tells us the cost, if you will, of transporting one field configuration into another field configuration. And the goal in the Kantorovich formulation, at least, is to minimize over transport kernels, which satisfy this marginalization property, to minimize over the energy incurred by this particular transport plan, where again, we have the amount of field phi1 that we're amount of the field that we're transporting from phi1 and phi to phi2, and then we have the cost of doing so. Now, to tie together the loop, the notion of the Wasserstein 2 distance, which we're going to require, is this one. So you can see that it's somewhat analogous to the Wasserstein 2 distance in finite dimensions, but instead of looking at the distance between two coordinates x and y, but instead of looking at x minus y squared, we are looking at the square distance between two field configurations, phi1 and phi2, where we're contracting with respect to an inner product, which is C lambda dot, where C lambda dot is the ERG kernel. What that means in particular is that C lambda dot is actually just the derivative of our cutoff function. So since our cutoff function is one which is equal to 1 below the cutoff scale and then dips to 0 at the cutoff scale, its derivative with respect to scale is going to be a function which is localized near momentum scale lambda. So in other words, the way you can think about this intuitively is that this is a Wasserstein 2 distance, which is penalizing us changing field configurations that are localized at momentum scale lambda. In other words, it doesn't particularly care if we rearrange field configurations which are away from momentum scale lambda, but it's basically saying that there's a particular cost, kind of like an L2 type cost, towards a reconfiguration of field theoretic degrees of freedom which are localized in momentum space at scale lambda. So the ingredients that we're going to require is a distribution of interest, on which we would like to perform renormalization group flow, namely P of lambda. So we have e to the minus s lambda phi, where we have an overall multiplicative normalization so that this probability functional is normalized. We also are going to require a background distribution. For the purposes of the Polchinski equation, suppose that this background distribution is just the probability functional corresponding to a free theory. Except that we're going to have a factor of 2 that will be important for later for a slightly conventional reason. And also let me define the relative entropy. This is just a classical relative entropy, but lifted to the space of probability functionals. So it's the integral over phi of p of phi times log of p over q. And I'll talk about what this means shortly. Now, more precisely, in the context of the Polchinski equation, this c of lambda dot is just the derivative of the effective propagator. So we see here the ordinary propagator, or the free propagator, I should say, times the derivative of the cutoff function. Now, when all the dust settles, we have been able to establish that the Polchinski equation can be written in precisely this form. So here we have, just to recapitulate, we have a derivative of p of lambda with respect to scale. And on the right-hand side, we have the Wasserstein 2 gradient of the relative entropy between p and q, where the background distribution q is essentially the probability functional corresponding to a free theory, albeit with a factor of 2. So this is an exact rewriting of the Polchinski equation. And it requires some synthesis of the ideas of the exact renormalization group, as well as this optimal transport story due to Otto that I advertised, and I'll make some comments about this shortly. Now you might say, well, how would you do this more generally for Oh, sorry. Yes, the punchline, of course, is that what this equation means is that the renormalization group flow is a gradient flow with respect to the relative entropy. That is the interpretation of this equation. More generally, we can attempt to study the Wegner-Morris flow equation. Now, the Wegner-Morris flow equation, superficially, when I showed it to you maybe 10 minutes ago, looked quite different than the Polchinski equation, and only reduced to the Polchinski equation in quite a special case. It turns out that to generalize this to the Wegner-Morris flow equation, we only have to make a very simple change. All we have to do is we have to generalize the background distribution. That is, we take Q of lambda, and we take the free action, and we just generalize it to a more general action, which can have some dependence on lambda. It can be some interacting action, for example, some interacting theory. When we do so, this generalizes to the Wegner-Morris flow equation. That is, the only difference in this formulation between the Wegner-Morris flow equation and the Polchinski equation is in the choice of this background distribution. Polchinski has it be a free background distribution, and the Wegner-Morris flow equation has it be a general background distribution. In fact, the choice of background distribution is tantamount to a choice of RG scheme. It is a way of incorporating scheme dependence. The different choices of Qs correspond to different RG schemes. So there are some differences between this story and the finite dimensional heat flow setting that I advertised to you in the context of the so-called Otto calculus, namely this connection between gradient flows with respect to entropy in the finite dimensional setting and heat equation. Some interesting differences are that the Polchinski equation is a reaction diffusion equation, and the Wegner-Morris flow equation is in fact even more general. So even at the level of finite dimensional equations, there is some generalization of the Otto calculus which is required. There's also subtleties, important subtleties I should mention, with the space of probability functionals, that the Otto calculus was really phrased in terms of finite dimensional probability distributions, and we have to really generalize this in several interesting ways to the space of probability functionals, which have their own difficulties. Something which is also important is the positivity of what's called the ERG kernel and its derivatives. In other words, there are certain features of that you might associate with the positive semi-definiteness of the Euclidean action and various other properties, which are actually essential for this derivation. So in other words, maybe said in a different, more Lorentzian way, there are features of unitarity which are baked in to this derivation working, that it only works for theories which would essentially be unitary theories, if you looked at their Lorentzian versions. Now, is a particular example of this to make everything concrete, let's consider the simplest case in which we look at the flow of a free scalar theory. So let's consider the context of the Polchinski equation in particular, where we look at the RG flow of a free massive scalar field. In this case, our flow equation simplifies. That the flow equation of a free scalar field theory under the Polchinski flow is just the gradient of actually the ordinary differential entropy. So what's special in the Polchinski equation is that the free theory actually flows not with respect to the relative entropy, but with respect to its own entropy. So what's happening, so let me go back for one moment, just to make a quick observation. Something which always puzzled me about the Polchinski equation is why there's this 2, why is it that this background distribution effectively has an e to the minus 2 times the free action? Why is that special, or why is that interesting? Another way of saying it is Polchinski's equation is just one particular example of an exact renormalization group flow. What's so special about it? Well, what I've shown you here, hold on one moment, is an answer to that question. It tells you that what is special about the one thing which is special about the Polchinski equation is that it is precisely the equation by which the free scalar field flows according to its own entropy. That factor of 2 that I showed you is precisely a factor of 2 that conspires to collapse the relative entropy into an ordinary differential entropy. Oh, is there a question? Okay. So what does the flow equation mean? So each step of the renormalization group flow, in fact, comes as close as it can to being a Wasserstein 2 geodesic, while simultaneously maximizing the entropy production as much as possible. I'll write this in a more precise equation later on, but this is an interpretation of what RG flow is. It wants to be a Wasserstein 2 geodesic, but it also wants to maximize the entropy production. Now, this is nice because this tension between being a Wasserstein 2 geodesic and maximizing entropy is something intuitive. We would like to think about renormalization group flow as facilitating a form of entropy production, that as we coarse grain our theory, we're increasing entropy. And this gives us a precise formulation of what that should mean. Now, why is the relative entropy appearing? Why is it needed? Well, the reason the relative entropy is appearing as opposed to the ordinary differential entropy is actually that entropy is ill-defined in general in the continuum. So let me just show you a quick example. Suppose that we consider the entropy of an ordinary probability distribution just on a discrete space, just a discrete probability distribution. If we try to generalize this naively to the continuum setting, namely P of I becomes D of X Px, then we see that we get a dx inside the log. At some other level, this is required in order to make the argument of the log dimensionless. So this is a problem. This is, in a certain sense, ill-defined. But one thing that you can do, which is better defined in the continuum, is that you can look at the so-called relative entropy. You can look at pi log of pi over qi. And when you bring this into the continuum, that essentially the dx's cancel out, you get px of dx over qx of dx. So now you just have px over qx. And now this is something which is well defined in the continuum. So this is a sense in which the relative entropy is a better quantity that generalizes the continuum as opposed to the ordinary entropy. So I'd like to emphasize again that the choice of the renormalization group scheme is encoded in the choice of the background distribution in the ERG kernel. That is, recall that there was this analog of Q, which was appearing in our relative entropy. The choice of Q is tantamount to a choice of the RG scheme. Let's now turn to the discussion of RG monotones. We've already said intuitively that we have provided a sense in which the entropy, or really the relative entropy more precisely, is a kind of RG monotone, at least in these for these kinds of statistical field theory type models. So now let's attempt to make this precise, that there's entropy production, that let's see if we can tie an RG monotone to the form of entropy production, which is suggested by the equations that I've written down. So the RG equation suggests that something like the relative entropy is monotonic under RG flow. In fact, it's convenient to define a slightly different quantity. Let's define m sub lambda of p of lambda as the relative entropy, where I'm going to subtract off this log of zq lambda. This log of zq lambda is subtracted out for a technical reason, which I'll explain in a moment. But all it really does in this formula is that it says that we're interested in the unnormalized version of the probability distribution q of lambda. So q is just going to be e to the minus some action and is not going to be normalized to 1. The reason we have to do this is related to the fact that we're interested in having a smooth cutoff function. Namely, if we have a cutoff function which goes to 0 and which is not smooth, then you actually don't need this log term. But we do need this log term if we do have a smooth cutoff function. Oh, was there a question? Maybe not. Okay. So what we can establish is that this quantity, this relative entropy with a simple subtraction, is in fact monotonic under RG flow. That as we take its derivative with respect to lambda, that the derivative is greater than or equal to 0. And in fact, this is a non-perturbative argument that provides us with this monotone. Now, the proof of monotonicity actually relies on the positivity of a functional analog of what's called the Fisher information, as well as some features of the exact renormalization group kernel, in particular our cutoff function. There's some subtleties that arise about the order of limits, which I won't delve into here, but they can be handled. This quantity, however, when we compute it in examples, this m lambda is often infinite, although its derivatives often have meaningful finite parts. So let me explain briefly how to tame the infinities of this object in a way which can be understood non-perturbatively. It turns out that non-perturbatively even, we have that the derivative of m of lambda with respect to lambda has the form of a delta d of 0 times a finite function. So we have, this is from some kind of contact terms. And we also have the finite term here that I'll call C1 of lambda. Now C1 of lambda, because the contact term is like a positive multiplicative infinity, the C1 of lambda should be greater than or equal to 0 for all lambda. And what we can do is if big C1 of lambda is an antiderivative of little c1 of lambda, which namely if minus lambda d by d lambda of big C1 of lambda equals little c1 of lambda, then we find that this big C1 of lambda is a finite RG monotone. So because of the divergence structure of this object, even if we have a multiplicative infinity due to contact terms, we can often find circumstances in which we can extract a finite RG monotone, just because the divergence structure is so simple. Let's do an example, namely a free scalar field, and then I'll talk about an interacting case. Here we can compute the RG monotone exactly, being careful about orders of limits. Here's an example of what the RG monotone is, at least this m of lambda type quantity, although I argued to you that that its derivatives are potentially better behaved. This quantity, at least superficially, is divergent actually for any cutoff kernels k of lambda. However, the derivative is better behaved if we look at its derivative up to this multiplicative infinity here, which is not particularly important. The derivative of log of k of lambda, in fact, this integral is in fact finite, and this can be shown to be greater than or equal to 0. So in other words, by looking at the derivative of m of lambda and extracting this finite piece, we can get something which is a better behaved RG monotone even for a free scalar field. As another example, let's consider lambda phi 4 theory. Let's just compute it in perturbation theory. Now it's going to be useful to develop a bit of notation so that we can compress the formulas. Let's define the effective propagator as k twiddle of lambda. And I'm going to define these three quantities, these three integrals, f naught of lambda, f1 of lambda, and f2 of lambda, which are various combinations of logarithmic derivatives of these effective propagators and various kinds of multiplicative combinations. And here we have computed perturbatively to loops the way that the derivative of the RG monotone with respect to scale, starting at some initial scale lambda naught, and it can be readily checked. This quantity, in fact, perturbatively in lambda is greater than or equal to 0 as claimed, as it ought to be. In the last part of the talk, let me turn to a variational formulation of RG flow. So first, let me tell you about a variational formulation of gradient flows. Consider the gradient flow d by dt of x of t equals minus the gradient of f of x of t. So this is just an ordinary gradient flow equation. Now, we can discretize this into steps. Suppose that we take t and we proceed by considering small steps of size tau, so that a single step, we can have this finite difference term and write this as minus the gradient of f evaluated at x of n plus 1 of tau. So this is like a forward difference type equation. This equation can be recast in a variational way, in which x of n plus 1 of tau is equal to the argmin over x of 1 over 2 tau of the difference between x and x and x of n tau, namely the location where x is presently, plus a penalty term of f of x. You can check just by taking a derivative with respect to x that if you will, that the saddle point equations or the Euler-Lagrange equations of this minimization precisely give you this formula. So this is a variational formulation of a gradient flow. So this allows you to determine x of n plus 1 of tau given x of n of tau and solving this minimization problem. Let's now talk about an application of this to renormalization group flow equations. Now, the Wegner-Morris flow equation tells us that if we do a step of RG flow, we can view it as a reparameterization of our probability functional. That is, if we start at some initial scale lambda naught and we coarse grain, we go to some new scale lambda naught minus t, then we can induce this by a reparameterization, which I'll call R of t on phi, which reparameterizes phi and changes the probability functional by a multiplicative Jacobian. It's going to be useful to call a reparameterized p, p super r of lambda. This is just saying that this is just looking at the reparameterization of p under r. This is just our compressed notation for the right-hand side. And the variational formulation of RG flow can be expressed in the following way. As we do a single small step of RG flow, we can express this as a reparameterization R of tau, namely reparameterized p, where we can solve for R tau by a minimization problem, where we minimize over the Wasserstein 2 distance squared between p sub lambda, the reparameterized p sub lambda, and our current p sub lambda, plus a penalty due to the relative entropy. What this means is that to do a single step of RG flow, to find rather the reparameterization of P, which will induce a single step of RG flow, that we perform a minimization in which we would like an R which induces P, the flow of P, to be a Wasserstein geodesic as much as possible, because if tau is a small step size, and this is the most important term in the minimization, but we pay a penalty in the minimization, which is due to this relative entropy. Now, a problem about this optimization in practice is that this minimization actually contains two minimizations. There's not just the minimization with respect to R, but there's a minimization of even computing the Wasserstein 2 distance. In other words, the Wasserstein 2 distance was also defined with respect to a minimization problem. Namely, it's an optimal transport type minimization. So it would be nice if there was a way of, in a more practical way of reformulating the RG flow problem, for which there's only a single minimization. There's not two nested minimizations. That would be much nicer. Fortunately, there is a way of doing so. So let f of
sorry.
tau.
I have a question. Can I ask?
Of course.
Just a few slides back, I think I'm still thinking something simple. Earlier, you mentioned this relative entropy as a monotone. I just want to make sure I follow what you say there. You say that RG monotone you define there, this quantity m lambda is defined non-perturbatively. Can you comment on that? Or what do you try to emphasize there to define non-perturbatively? It's like maybe 5 slides earlier.
Yeah, oh, sorry, okay. Well, let me maybe make some comment about it, and I can go back to the equations if we need to do so. So
Okay.
the answer essentially is that the Polchinski equation and the Wegner-Morris flow equations are non-perturbative equations for RG flow. And the arguments that are used to show their equivalence with this Wasserstein 2 gradient flow are arguments at the level of the path integral. They're functional, I mean, insofar as the path integral makes sense, they're non-perturbative arguments for the equivalence of the equations. The point is that the derivation of the RG monotone is done at the level of the non-perturbative essentially flow equations. It is a formal property of the non-perturbative flow equations at the level of functional integrals. And insofar as those manipulations make sense, then it should be an RG monotone that is defined non-perturbatively. In other words, it makes no assumption as to the small couplings or changing the RG scale by a small amount. It's just an intrinsic feature of the non-perturbative flow equations as I've written them.
Okay. Say this.
Sure. So let me go back, but we can return to that in a little bit. So let f tau be a reparameterization on the space of field configurations. We can also think about RG flow as a push forward under a reparameterization. That P at scale lambda minus tau is the push forward of P under f of tau. So we're thinking in the previous slide, we've done the inverse of this. In a certain sense, we've thought about a reparameterization R, and we can think about F as the inverse of R. So in other words, it's just more convenient to reason about reparameterizations in terms of push forwards as opposed to these R-type quantities. Now we can establish that the variational formulation of RG flow only has a single minimization. That to get the f of tau that brings you from one RG scale to another, you simply have to perform a single minimization problem where you minimize over 1/2 tau of m of f, where m is the Monge functional, plus the relative entropy between P and the reparameterized Q of lambda, reparameterized by F. What's nice about this is that, as I said, there's only a single optimization. And once you have the F of tau, it gives you a nice way of sampling from this new distribution. So suppose that we have sample access to the original distribution P of lambda, namely we have a way by which, say, using Monte Carlo methods to sample a field configuration phi. If we have an explicit expression for f of tau, then there's a simple manner by which we can sample from the push forward, namely which will be P at scale lambda minus tau. The way you sample from the push forward is that you just sample a phi from the distribution P of lambda, and then you map phi to f of tau acting on phi. And this will now give you a sample from the push forward, which will give you a sample from distribution now RG flow to a shorter moment, a smaller momentum cutoff. Now, the utility of this is quite interesting in numerical applications. So here is the expression really spelled out a bit more for what it is that we're going to minimize. Let me write it in more compressed notation. We can write this minimization for this f of tau as an argument over an expectation value of some quantity we call a loss function in the parlance of machine learning with respect to samples from phi. That there is an average of the loss function over samples from phi. Now suppose that we parameterize the reparameterization f in terms of a finite vector of parameters theta, which have a differentiable dependence. Namely, the manner in which f depends on theta is differentiable. Then what we want to do effectively is to perform a minimization over theta of this expectation value of the loss, the so-called loss function. This is just a way of packaging the minimization problem of this functional of f of theta, its functional derivative in p as well as q. Now, for those of you who have some experience with machine learning, you'll immediately notice that this is precisely the form of a optimization problem which is amenable to performing what's called stochastic gradient descent. Moreover, we argue in the paper that a good ansatz, in fact, the correct ansatz, the correct form for this f tau theta to have is that of a convolutional neural network. In particular, if we have a translation invariant field theory, the form that we would want this reparameterization to want to have the right equivariance properties under translation symmetries is precisely that of a convolutional neural network. What this does, if when spelled out a bit further, is it provides a precise connection between the renormalization group flow and convolutional neural networks in a manner that can be made completely precise. Let me conclude with the discussion. In summary, we've established that the Polchinski equation, more generally the Wegner-Morris flow equation, is the optimal transport gradient flow over relative entropy. We've shown that RG flow has a surprising information-theoretic formulation involving the relative entropy, but also crucially cast in terms of the optimal transport formulation of convection diffusion equations. We've also found a new non-perturbative RG monotone. We've established a variational characterization of RG flows, which is amenable to numerical methods, and in particular using some amenable to contemporary techniques in machine learning. There are various generalizations in future directions that would be interesting to pursue. For instance, it would be interesting to generalize to a richer class of field theories, for instance, with fermions, gauge fields, etc. In the context of the Wegner-Morris flow equations, this was carried out by Morris and various of his collaborators in the early 2000s. And it seems extremely plausible that most of these techniques will generalize the context of these optimal transport type formulations of RG flow. An interesting possibility is because we have so much flexibility in our RG flow scheme, namely this choice of this background distribution Q, it seems that it's possible that a judicious choice of Q allows us to potentially constrain signs of couplings in the effective action. What I mean by this is as follows, that our RG monotone allows us to have a certain sign constraint on various integrated quantities in the effective action. And perhaps by choosing a judicious choice of RG scheme, maybe one that would be unnatural from most points of view, except to be natural from the point of view of this problem that I'm telling you now, is that we could choose a weird RG scheme, which would allow us to have a positivity constraint on couplings in effective field theory. Now, as I have suggested in the last part of the talk, it would be fascinating to pursue numerical methods, for example, based on stochastic gradient descent, for the renormalization group flow based on the sampling of the Wasserstein gradient flow. Also, for those who are familiar with Maras, or this is a particular type of tensor network, it would be interesting to use reverse gradient flows as an ansatz for continuous Mara tensor networks. For those who are familiar, I'd be happy to speak more about this during the questions. It would be nice to have a holographic interpretation of this. Is there a way in which this formulation of RG flow with respect to relative entropy tells us something in the context of ADS-CFT? And finally, it would be nice to have a further information-theoretic understanding. There have been various papers across the last 10 years which have provided interesting information-theoretic commentary and interpretations of RG flow, albeit not ones that connected to the Wasserstein distance or to optimal transport. These ideas, however, were extremely interesting, and it would be fascinating to correct them, not to correct them, but to connect them in a more precise way to this formulation of RG flow using optimal transport that I presented here. Anyway, with all of this in mind, thank you so much for your attention. Of course, happy to answer any further questions.
Thank you, Jordan. Question from the audience? Feel free to speak up. Maybe let me begin with a naive question if no one want to ask first. Actually, wonder, say, for example, if I'm particle field theorist, maybe care about some scalar field potential, possibly just some kind of Higgs, or maybe some beyond standard model scalar fields. And we know there could be some phi square, phi full term. Suppose I just want to make sure that, and these are one thing that maybe people care for this boson theory, and maybe for statistical mechanics in condensed matter system, maybe people can write down some more complicated forms of equations, and possibly with some interpretation for more complicated interaction between the scalar fields. And I was wondering, say, whether your formulation can tell them something more than the previous old RG formulations. Maybe you can suspect something like maybe we'll benefit from these formulations.
Yes.
Something like,
yeah. So let me make a few comments to that effect. So
something beyond textbook people know. Yeah.
Yes, great. So a few things to say is, on the one hand, I should mention the fact that we did this for scalar fields was just, I don't think that that's a fundamental instruction. It was just out of simplicity. There was already sort of enough to deal with in the level of scalar fields. But I think that having worked that out, that introducing fermions and gauge fields using ideas that Tim Morris and other people have developed. So let's assume for the moment that we can do this for more interesting field theories, say. Well, I think that, to me, what would be really fascinating, which is something that I've been currently thinking about, is to use this to develop new non-perturbative numerical methods to look at interesting RG flows. For instance, we can start with a theory, for example, in the UV, which we believe should flow to a pretty non-trivial IR fixed point. And the question is, how do we actually efficiently have sample access, for example, or rather be able to compute correlation functions or aspects of a non-trivial theory in the IR, given access to a UV theory with some perturbation that will flow to that IR theory. And there's just not that many techniques for being able to do that non-perturbatively. And I think that some of the numerical techniques that I was suggesting at the end are potentially so efficient, or have the promise of being so efficient, that they would allow you some potential access to those theories which are at the end of non-trivial RG flows. I think that, to me, would be the most interesting thing. But there are also more structural questions. For instance, I think something that could be conceptually interesting would be understanding how this interfaces with holography. The context that I'm interested in holography is not the conventional setting of ADS-CFT, but there's been some ideas proposed maybe 20 years ago by Andy Strominter, as well as Edward Witten and various others, about ways in which you could conceive of holography in the context of de Sitter space, namely with a positive cosmological constant, something more apropos to our own universe. And there, you essentially have some Euclidean, although potentially non-unitary theory, which is a Euclidean theory, which is dual to quantum gravity theory, where there's an emergent dimension of time is instead of an emergent direction of space. And in that case, the time evolution, the direction of time, is dual to the RG direction of the dual theory. And I think that there's actually some very interesting connections to this formulation of RG flow that I've presented here, and to some understanding of the emergence of time in the context of a putative de Sitter CFT correspondence. So I think those are two interesting directions among others that I'm interested in. I think the numerical one would just be a very nice tool to have to understand non-perturbative RG flows. The other one is would yield more conceptual insights.
Thank you very much.
Sure.
Actually, let me ask one more conceptual thing. I just want to make sure the reason you say this is non-perturbative, but the equation still written in the sense of maybe it's kind of like differential equations governed by perturbative calculations. Is that the non-perturbative reason is that you can identify some monotone quantity that control the RG flow in a larger scale instead of just perturbatively? Is that the reason you emphasize non-perturbatively, or is there something else I missed? Maybe just
let me maybe say it this way. It's that the derivative of this quantity with respect to lambda is greater than 0 for all lambda, not just at the initial lambda, but for all lambda. So in other words, it doesn't just work perturbatively around the initial lambda; it works for all lambda along the flow. So that's the sense in which it's not perturbative in lambda. So, yeah.
Another question from Hank.
Yeah. Thank you for the very nice, interesting talk. Actually, I have, I guess, one fundamental question and then some other questions related to that. So my first question is, so you mentioned along the way that, for example, picking what Q is, right? The big Q functional essentially means like there are different RG schemes that you can pick to compute your, for example, the monotone quantities and your RG flows and stuff like that. So is it true then that if I pick different Qs, right, and then there are different, for example, picking one Q, one form of Q, for example, picking one RG scheme would give me more RG monotones than picking another one. Is that possible?
Yeah, so let me maybe rephrase the question the following way. So one thing you could ask is, you're asking about scheme dependence of the RG monotones.
Yes, yeah.
So something which has been studied by Morris and his collaborators, at least in the early 2000s, was in these exact RG flows, how which kinds of quantities are scheme dependent and not scheme dependent. So they, for example, I believe in the context of QCD, they showed that there are certain class of RG flow schemes for which you can compute beta functions or correlation functions, which in a certain sense are scheme dependent within a certain subclass of these choices of Qs. So the answer is that I don't fully know. Of course, if you've ever thought about how to perform RG flows numerically, for example, in statistical mechanical system, there's many different ways of doing coarse grainings, different decimation schemes, different coarse graining schemes, and so on. And the hope is that, the question is, for example, if you're interested in reaching some particular interesting IR fixed point, then you ought to do this with a particular type of scheme that you think will allow you to hit that fixed point. I think it's the same kind of thing here. I think that I don't yet understand in full detail exactly how the importance of the scheme dependence of the RG monotone, but indeed you are correct that there is at least some scheme dependence in the RG monotone, sort of by definition, that it depends on Q. But the point, however, is that there might be different classes of Q, not the most general classes of Q, but a few, say a family of Qs for which the RG monotone is in certain aspects insensitive to the choice of Q within that subfamily. That's something which one could hope for and which would be commensurate with some previous results by Morris and others. Hopefully that at least partially addresses the question.
Yeah, it does, because that's very interesting, because I have there are formulations of point of gravity where we study, basically treat QG, like some theory of QG as like a UV completion of some effective field theory, for example. And then we use that notion to constrain what the UV theory has to be. So as you said, like if there's some scheme dependence of, let's say I start out with some EFT and then there's some scheme dependence of how we go from the UV to the IR, where you have like a UV point of gravity, then that would be kind of, I don't know, kind of bad, right? Because that just introduces more things that we don't really know and we don't really have control over in the sort of like the realm of asymptotic gravity.
Yeah.
At least from that perspective, yeah. But yeah, if there's some control over what kind of schemes to actually have the right sort of classes of monotones, then yeah, that would be very interesting too.
Yeah, well, I'd recommend looking at these papers by Morris on SU Yang-Mills theory from early 2000s. They talk more about these issues.
Okay, great. Yeah, I'll just send them to my colleagues because I don't do asymptotic gravity, but they do.
Maybe you can go on with the second following question. Thomas Schiffer, please.
Yeah, I have a kind of related question, which is again my naivete. So there's been a fair amount of work over the years on exact renormalization group equations and sort of statistical mechanics kind of models.
Yeah.
And there's also been a fair amount of work in gauge theory, except that was always kind of confusing for I think two reasons. The first one was that in practice, you always have to fix the gauge. And then the issue was that you somehow have to parameterize gauge non-invariant actions. And there didn't seem to be a kind of systematic way of doing so. And the second puzzling issue was always that in QCD, for example, we have a strong belief that ultimately the effective action is theta dependent, but theta dependence requires somehow large gauge fluctuations. And if I solve some kind of renormalization group flow, where in every step I only integrate out small fluctuations, then it seems like I can never generate theta dependence. Is there any understanding of or any progress on these issues?
Yeah, that's a good question. So insofar as I understand, so I don't know about the second part of your question. I mean, that's quite interesting. I mean, the nice thing about ERG is that at least it should, in principle, be the right kind of framework to address the latter half of your question, because of course you're going to ultimately integrate out much larger fluctuations. I mean, it's a non-perturbative question, in other words, at least in terms of the size of the fluctuations. But my understanding was at least that the first set of questions that you said got resolved, or at least mostly resolved, in a series of maybe papers over the course of 10 or 15 years, starting with Morris, but then and his collaborators, but also carried forth by other people as well. So I can't comment on the specifics of them, but I could try to dig up the papers that I think provide the most state-of-the-art answer to these questions about how to deal with gauge fixing, and in the context of, these kinds of things that you were asking about in the context of ERG. But perhaps perhaps you're familiar with these works and find them unsatisfactory. I'm not sure.
Yeah, I mean, if you could maybe forward to Juven or put it in the chat later of what you think is kind of the best reference on that, that would be nice.
Sure. Yeah, I can do that. I can just send it to you. Great. Yeah, thanks. I'll do that. Sure. Thanks.
Thanks, Thomas. And I think Sayak has a question. Sayak, please go ahead.
Hi, thanks for the talk. So this is a very broad question in that it doesn't pertain to RG theory, but okay. I recognize the things that you've been talking about. It's very similar to something that's been noticed in evolutionary dynamics, where you have these nonlinear equations that govern the dynamics of a population, and that has been shown to be equivalent to a gradient flow with respect to what they call a Shah-Shahani metric, which is basically equivalent to the Fisher information metric, which you might be familiar with. And the gradient flow is with respect to some potential function. It's kind of like the energy functional you were talking about for the heat equation. So, and what's interesting there is that you were using the relative entropy. And in that theory, it has been shown that since this is nonlinear dynamics, you have a Lyapunov function to define stability of such systems. And the Lyapunov function there happens to often be the relative entropy between two probability distributions of those population systems. So I was wondering if you are aware of this, if there are connections, what's the broader idea? If you could make any comments on that.
Yeah, well, I wasn't aware of this work in evolutionary dynamics. I mean, perhaps you could, if there's any relevant papers there, maybe you could send them along in an email or put it in the chat. Yeah, I'd be curious to read about it. I mean, at least to me, like, you know, there are many different, there's many different kinds of dynamical systems which are natural to write down, which are gradient flows in the sense of Fisher information, or are related to this optimal transport business, you know, due to the work of Otto and other people. But, you know, I don't immediately know what to say about the connection to that, but I think that, look, I mean, you know, if there's another way of writing in the RG flow equations, for example, that gives us another way of thinking about them or another way of interpreting them, you know, maybe there's some interesting evolutionary dynamics interpretation that would surely be very interesting, even if I don't immediately see what the line of connection is. But I just want to point out that these kinds of flow equations are somewhat ubiquitous in the sense that there's many, you know, there are many different kinds of PDEs which secretly can be written in this way. So it's not surprising that there's other examples that kind of occur in kind of disparate circumstances, but I can't say anything about what that means for the interpretation of RG. But maybe there is.
Thanks for that. I'll probably hit you with an email sending some references. But I was wondering if you could point out what sort of advantages do you see with regard to reformulating this problem in the information-theoretic framework, apart from, say, the numerical advances you could do using techniques from machine learning and stochastic descent and so on? Are there understandings like with regard to stability or fixed points or something along dynamical ideas that you could gain through information theory?
Yeah, so, well, yeah, so a few things. I mean, one of them is in the derivation of the RG monotone. It uses some of the properties of the relative entropy. So that's at least one kind of concrete thing which we did. But you know, another thing to say is that there's this whole literature of, you know, I don't know if you're familiar with these things in PDE theory called the log Sobolev inequalities. These are particular kinds of equalities on infinite dimensional, well, I mean, they're most useful in the context of infinite dimensional probability distributions, which were kind of inspired by work in field theory and had been appropriated into the context of just high dimensional probability and statistics. You know, there's this whole world of inequalities that involves relative entropies and flow equations in various forms. And the advantage to using these information theoretic ideas is that it allows you, that there's a lot of tools which give you analytic traction on potential features of RG flow beyond just the monotone. For example, you can think about, the reason I mentioned that is that the log Sobolev inequalities has relations to the convexity, for example, of a saddle point. You know, you could look at, for example, the curvature of the Hessian, for example, around some saddle point of your Euclidean action, and you can use various information theoretic properties to get you bounds on features of the convexity. So anyway, so it just opens up a tool set that I think will be very useful, that has been leveraged by people in PDE theory and high dimensional probability theory already, that we can now port into theoretical physics and see what we can do with it. But I'm not sure at the moment what to say beyond the examples that I've stated.
Right. Okay. Thanks. Thank you very much.
Thank you.
Arthur has a question. Arthur Cosmala.
Thanks a lot, Jordan. Very interesting talk. So something I was wondering about was you had this loss function, which I think was the sum term of the Wasserstein distance and the relative entropy between those probability. Anyway, so I was wondering how you would go on in the practical numerical case to evaluate this loss function, because in the machine learning case, you kind of have your training data and you can treat that as giving you a Monte Carlo estimate of the loss function, kind of sampling this training data from the unknown actual distribution.
Yes.
And here it's kind of, you don't have this training data. So how would you go on in practice? I mean, if perhaps you might have some insights how that would work in this case.
Yeah, so the way this works, the formulation which would be best to use is the second formulation I said, where you use the you don't have to do this double. The Wasserstein distance isn't involved. You just use the Monge functional. But in any case, the way you do it is that you suppose that you have via Monte Carlo methods, maybe you have a lattice. You have sample access to your theory at some initial scale lambda. Sample access. So you say by using Monte Carlo methods, and that sample access is sufficient to essentially what you do is that you use stochastic gradient descent to derive or to find a convolutional neural network which provides you with the push forward under which your initial distribution will become a probability distribution over the flowed theory. So there's no data per se. It's just kind of, when I say using techniques for machine learning, I just mean it's just like, it's optimizing a convolutional network, with respect to a certain loss function, and with respect to a certain, how do I say, a certain distribution that you're sampling over, which is the probability distribution at the initial scale. So that's the sense in which it fits into that framework. That's how it would go.
Interesting. So in a sense, it is similar to machine learning. So you don't really have data, but still you kind of sample from this distribution now using a Monte Carlo method. And this way you generate a Monte Carlo estimate of the loss function and can minimize that using the machine learning model.
And the nice thing, of course, is once you variationally solve for this reparameterization, it's easy to sample from the push forward, because that's the nice thing about push forwards. Yeah.
Thank you.
I think there's another question from Amanov.
Mr. Cotler and Mr. Wang, I just wanted to really thank you for the wonderful webinar, particularly that you offer the great opportunity for all people around the world to learn about advanced concepts from quantum physics. It's a great honor. Thank you a lot. Just this comment.
Oh,
thanks again.
It's very kind of you. Thank you for attending.
Any other question? Physics or math? If not, let us thank Jordan. Thank you very much. Let me just also mention, I think if you still have interest on related topics, actually, Jordan, I think you will be speaking something maybe even more broad. And if people are interested, I think you can contact Jordan and maybe he can follow up. Anyway, but
later this afternoon for later this afternoon, there's going to be some other seminar where there's going to be a tutorial on optical transport in the auto calculus.
Thank you. If you're interested, feel free to attend. All right, so thank you, Jordan. Bye-bye. See you.
Thanks again for having me give the talk. Thanks.